Okay, before I want to solve for this, before I continue, I would like to make a very clear, message for our FPD free body diagram. So as I mentioned, this x2, x0, and x1 is never I make another anyway, it's never uh, the same as this x1. Okay, it's not the same as this x1, it's not the same as all whatever x1, whatever thing that we are deriving for the x1 is actually the motion minus kx. Okay, this x is just the position. Okay, it's just the position. You can take it as a datum, I would say. So maybe I would define it properly. So it will be x, the variable x2, and the variable x0, and the variable x1. And then minus kx is actually the x. Okay, maybe I should put over here 4.5 minus kx1, and then 4.6. Maybe I shouldn't put 4.5. Hold on a while again. So as you pull this thing over here at this point, so at first your datum is x0. And when you pull it up to position x1, so x, the variable x is actually the position. But when you release, when you start to move, when you release the whole thing start to move, there will be a spring constant multiplied by x1. This x1 is actually the distance between wherever you're actually comparing. The distance may be this x. Okay, so this x can be x1 also. So that is x1. Yeah. So apparently this x1 is not the same as this x1. This x1 is the position. This x1 is the distance. Okay. So I hope I made this clear. So this is the distance. This is the position. Okay. So and then the whatever thing that I'm talking about the x1 here is actually the distance. I'm talking about the distance. To make this very clear, I'm talking about the distance moved. Okay. So with this said, let's continue with the differential equation. We last stopped over here. Okay, we actually combine. Actually, we haven't combined. We just derived the particular integral f over k, if you remember. So if you also remember that we have a differential equation. We have a complementary function plus the particular integral. And then we have our complementary function over this is this one, and then we solve for the particular integral which is f over k, and then you combine them together, you have this thing over here, our general equation. So now we have to solve for our a1 and b1 because we want it to be a defined one so that we can actually continue other steps. So thus we need boundary condition to solve for a1 and b1. Okay. So the first assumption is that when t is equals to 0, x dot when time 0 is equals to 0. So what it means is that when time is 0, the position, when time is 0, just before you release is over here, right? When you start to pull here, and then you reach at x1. Before you release is actually t equals to 0. So if you were to remember the graph, we have this over here, then before you release is over here, and then when you start to release, it goes down, and then you start to oscillate, you know. So I'm talking about that. So when time is actually at 0, is actually this point, okay? And then the move, because when time is 0, you didn't release anything, right? You didn't release the mass, so there will be no velocity, right? So therefore, this x dot when time is 0 is equals to 0 because it's not moving at all. Okay, when it's moving, then seriously 笑了 lah. But anyway, x1 is equals to this equation over here. Okay, it's the same thing. We differentiate one time, we get this equation over here. And then now we sub in our boundary condition when t is equals to 0. When t is equals to 0, cosine 0 is equals to 1. Or sine 0 will become to 0. And since this dude over here is equals to 0, so this one becomes 0. Okay, x dot 1, 0 is equals to 0 because no velocity right? No velocity, that's why 0 also, because as defined here, I think you know already. So this one will simplify into here. And from here we know that a1 is equals to 0 because our natural frequency cannot be 0. If its natural frequency is 0, that means there'll be no such case. You have a spring, definitely you have a natural frequency, you are dead. Anyway, so yeah, I'm a bit 笑了. Anyway, so second assumption. So we solve for a1 already. Now we solve for our b1. Okay, we solve for our b1. Our b1 over here. So our b1 is actually when t is equals to 0. Same thing, when before you release, your position is at x1. Okay, I have to make it a bold. You give me a minute. Hold on. Okay, so position x1 is not distance x1. Okay, be very clear. Okay, I just realized my mistake. And then let's continue. So this distance x1 is dependent on x1. Okay, the position where you start. Where you start is dependent on, because this is your datum point, you take reference from this datum point x1 and then you get the distance. Okay, so equals to a1 sine omega, which is the general equation, which is this one. And then we sub in our t is equals to 0. And therefore we have because this one will eventually go to 0, and this one will become plus, because cosine 0 is equals to 1, so b1 only, b1 plus fk. Okay, and then this also should be, yeah, hold on, should be a very bold exposition. Okay, so this is position x1 is equals to, we just rearrange, I mean not rearrange but sub in. Okay, the distance x1, because since time 0 it didn't move, so its position is at x1. Okay, it's at this point. So I hope this sinks into you. So when you start to move, there will be a distance x1 right? There will be a distance x1 along all this stretch Okay, yeah. So you can say that this distance can take on any form of distance x1, as long as wherever you want it to be. So this is x1. Okay, from this point to the very end point. Okay, you know what I mean? Okay, I think you know what I mean. This is the point where it didn't compress anymore. It will start to spring back. So this is the point where it's the lowest point. Okay, lowest point on the graph. Okay, lowest point is at this point already. You cannot keep going further. So once you're at this point, you spring back. That's why there's will be. Okay, I've done a lot of touch up already, so I hope you get it clear. And then once you get that, you eventually get this one. You just change to b1. You'll find your b1, and then now you sub in your a1 and b1 into your general equation. This is your general equation. Perhaps I can say that this equals to x1, the distance. Okay, the distance again, not the position. And then now you sub in the a and the b. You have this thing, and then plus the particular integral. And tada, you have your distance. This can be computed by this formula. where this is the position. As I said earlier, everything starts from a datum, so this is the datum I would say, x1, okay? So you take reference from this x1 over here. So I hope this clears up, and take note that I haven't finished yet, okay? I only finished one part only. As I said earlier, it's from right to left, okay? When you release it piam, and then pum. But now for the next video, it is from here and then pump back here and then start to oscillate to equilibrium. So I will see you in the next video for the second part of the series.